This video will continue our discussion of conservative vector fields and running a line integral over with a conservative vector field. All right, so we have a definition here. This is a beautiful thing if they are conservative. So let R be a region in R2, R3. Let phi be a differentiable potential function defined on R. And then we're saying here, we're saying that f is conservative by saying that if I take the gradient of phi, I get f. Then I have this definition. It's pretty nice. I'm going to prove it to you. So we'll prove it, and then I'll give you a different way to think about it. So what this is saying is if I have this set up, right, which is what we've been working with here, we actually can just plug in phi of b, our points, our top point minus our bottom point. So let me prove it to you, and then I'll give you a way to kind of make sense in context. You've seen something like this before. All right, so assume that f of xy is equal to gradient phi of xy. And then we're going to label this phi x, that's that component, and this is phi y. All right, that's how we would derive the gradient, right, calculator. Okay, so then, if that's the case, then c, the integral over c, the line integral over c dot dr is going to be, all right, we can break this up using something from Calc 1. This is the chain rule, creating a chain rule, dr dt times dt. And then that inside there, this is going to take a little bit for us to really get the idea. Now, I want to make sure that you know that r of t, our path, is defined x of t, y of t. We need to state that because we're about to write something here. Okay, that means dr, right, equals x prime dx plus, I think it's going to be comma actually, because it's still a vector, and then y prime dy, dt's. All right. Okay. So, but we have that there. So what we're going to do now is we actually can rewrite this as, okay, well, it's going to be the phi function with partial with respect to x times, if we are dotting f and dr, this is dr, right? We have times x prime of t plus, and then our dot product would be phi with partial with respect to y of y prime of t, and then this is our dt's. We were good with our dt's. Okay, cool. So that's where this comes from. Dr is this vector, and we were just dotting that with, where did we define? Right here. We were dotting it with that. Now this is going to be the part that's a bit difficult to see. This is the, and you may not be able to see it the way it stands, but if I were to rewrite it like this, just like that, maybe that rings a bell. This is just the chain rule. So this is actually just d dt of phi of x of t, y of t. That's just the chain rule for that. What makes this great, and this actually proves everything for us, this whole thing, integral of a derivative, gives me phi of x of b, y of b. We'd plug b into x and y, and then plug that into phi. And then we would minus phi of x of a minus x, comma, y of a. And that would be our theorem, right? It's all based on this chain rule idea right here that breaks our integral down for us. It's kind of a neat little proof. So I'll put a little box. I used to put lines. It doesn't matter. Okay, so we proved that theorem. One thing I want you to write down also as well, why this theorem makes sense. Our gradient is a derivative in some sense. So think Calc 1. Let me write this down, and then hopefully it'll come back to you. If I take the integral of a to b of the derivative of a function, but it's the derivative, and we want to put a, let's put a t there, that's fine. Put a t there, dt. Well, how this works out is the derivative of the integral undo each other, and we would get the function itself of b minus the function of a. But with my that's it. So in this sense, this would be like our phi here, and then this would be our gradient of phi. There's no prime here, by the way. Cool. That's what it was. You could think about it in this sense too. Sorry for the silence there for a minute. Another way we could write this is like this. Right? So that's where I got mixed up. The integral of the derivative, the top line still means the same. This is f of b minus f of a. There we go. Okay. This whole thing kind of threw me off. This is a derivative in itself. So that whole thing is like the gradient. And then we get phi. Or we can even think about it down here. Let me rewrite it. This is like the gradient because the gradient is a derivative. And then these are just the functions that came from. Right? The potential function that we just had to plug in. Right? We're going to do several examples of these. It will get better with context.